So this is a neat little demonstration of the control circuit I'm using. M is the driving voltage. This up and down signal is the actual wheel speed, and this flat line is the desired wheel speed. And you can just see how that, it keeps bouncing as it goes low, so M shoots up, goes low, and then it goes high, and M shoots down, and it sticks around there pretty evenly. Transient stuff, very weird. I'm going to try to make this better though. And here that is again, but now we have the error, which is the difference between the input and the output, projected in yellow down here. Watch this start up. See, that's way too long. You can see the error shoot up, come down, as the voltage in the motor driver steadily goes up until it reaches transients. I'm just gonna take out this divide by 50 and see if that helps, since that is, we're dividing the error by 50 before we use it, so this should be interesting. Definitely more oscillations in there. Oh my god. It's probably not good for the motor. Holy smokes, Batman. Okay, what if I go and grab it? Alright. Whoa. It stopped. So this is an example of, I guess, an underdamped system. You can see these oscillations just growing. It's definitely not good for it. That wheel. And then it goes back to normal. This is a great example though. I love this of just really, oh, there it goes again. Programming or coding meets the, like physical objects. And you've its speed, its desired speed, its error, and the driving power. That's not good. I gotta stop that. Those oscillations are coming from me squaring the error, so as the error gets really big, that's the amount we change the driving M magnitude by, and it's squared. So, if the wheel is spinning twice as slow as where I want it to spin, it will have 4 times the push, as if it was spinning like, I think 1/2 as slow, something like that. But I moved the damping up to 40, so. See, it's actually pretty stable. This is from when I just held it though. See, I can't stop it, which is good, that's what I wanted, but oh, it doesn't like that. That's weird. Alright, I doubled it from 40 to 80 and I think I solved the problem. Watch when I try to stop the wheel. I can't. And then the oscillations go away. See, this is me holding it. And you see the blue, the power goes up because I'm giving it friction. And then I let go of it suddenly. That power drops because it doesn't need it. It smooths out and autocorrects. Good work. It's like I have a team of small midgets in there just driving. So this is probably a bad idea, but I'm gonna put the error to the 3rd power. But I turned the damping up by 150%, so no chance of failure. There's transients. There's the air. There's the driving voltage input to the motors. The smooth line is the, oh my god, no, Jesus Christ. More damping. These are quite forgiving Segway motors. So. That's 800, let's see what happens. So it's attenuating the error by 800. but the air is cubed, so. All right, no crazy oscillations. Good power, way below error. This is the desired. Here's the actual. That seems pretty stable-ish. See if it freaks out when I try to stop it. Oh yeah, it definitely freaks out. Does no. All right, I think I'm gonna stick with squared, but I moved it from 80 to 100 for some safety margin, and then I'm gonna plug in different power levels and see how it goes between the two. But this test, this hypothetical I'm doing right now, which kind of simulates the starting torque, where I just clamp it with my hand and let go of it suddenly, is not very realistic. You know, mostly you'll have clamping, and then once it starts moving or it goes over a hill or something, it won't be such an instantaneous shock to the feedback system. So cool, but it's good that it works with it anyway. All right, so I changed the feedback system so that basically if the wheel spins slowly, make the change rate steeper, and if the wheel's spinning very fast, no need, make it smaller. So you can, oh, already open. What the hell? So now, there's the error, there's the input, there's the desired, and there's the real. Whoa, look at that, that was weird. But you can see the desired and the real are pretty similar, and they cross. That's weird, that's weird, that's weird. I don't know what that is, but I probably have to move the threshold. That's pretty cool though, in terms of feedback and control. Probably if I move this 500 back to 200 or 300. Alright, let's see if that fixed the problem. Alright, any weirdness? Oh, that's so much better. Look at that beautiful sine wave-ish. I guess this would be your more accurate output, desired output. This is my desired input, it's a sine wave. It's a little bumpy. But this is the real world. You can see the error spike up and it crosses over that transience. It's not really linear because you know your amplification's kind of different in different places, but it's okay. It's good enough for government work. I found out why the communication signal is so dirty for the BMW communication. See if you can find it out. Here we go. Pin 11 is our output, right? We analog write that. Now why would there be anything wrong? I slashed out now, you can obviously see, but oh my god. I've been like, why is it so dirty? Why is it so dirty? This is the final iteration of my control code. You can see the target and the actual follow each other quite nicely. And this is an example of me switching through the on and off states. So when it zooms forwards, that's the off state. There's just a threshold right here. And that's important because moving in and out of on and off states, this stuff is challenging before. And then here's the error as it was before with the gold on the bottom. So I broke the feedback code into 3 different boxes, all depending on basically how fast the wheels are spinning. So if they're going real slow, take the error cubed. If they're moving a bit, take the error squared. And if we're just going, just take the error. So yeah, and then I also take all 3 tachometers on the wheel and I average them right here, common filter them, take the absolute value, and that's how we get our error. And this is for the plot right here. And we write to the DAC for the output voltage for the wheel control. Whoa. What do you do? Alright, cleaned it up a little bit more. And right now, this is a really, hard input signal to follow because it's instantaneous. You see, it follows it really good at speed. And then at slow speed, it's a little more noisy in areas, you can see, but it almost sticks with it. It's almost vertical to its line of acceleration, then deceleration. Cool. So I hope you guys all like that. This is the third edition of the controller board. So hopefully it works out.